how valve works. Okay. So let's say first initially you assume that this is insert type pump. Insert type pump means you have barrel here, you have one travelling valve, is standing valve, then you have barrel here, you have travelling valve, and you have sucker rod. Okay. So this is SV, this is TV. Okay. Now I will be assuming different pressure here, P well bore pressure or tubing pressure is there. Okay, you are anchoring here, and this one cylinder pressure, and this one may be plunger pressure, P plunger, P cylinder, and P, what will you say, P tubing. Okay, P tubing. Okay, when fluid is lifted, so that pressure will be P tubing. Let's say initially assume your travelling valve and standing valve position like this. Okay, travelling valve is at lowest position. Okay, if you see this beam pump one, so it is at the lowest position. Okay, it is the lowest position and it is stopped. So what will happen that time, this valve is closed, this is also closed, because this is not running, the beam pump, that plunger coming to the bottommost position, and both valves are closed. Now this area will be almost sealed. Okay, there will be no leakage, we are assuming. Okay, so no leakage, almost no leakage. Okay, there will be some leakage, so we are assuming almost or negligible leakage. At the bottommost position, both valves are closed, TVSB. Now after, let's say 2 seconds, after 2 seconds what will happen, this plunger will try to move up. Okay, so initially this distance was there, I am assuming this is valve cage distance. Okay, now this distance little bit increased after 2 seconds. Okay, so after 2 seconds what will happen, plunger is moving up, this is moving up. Okay, after 2 seconds plunger moving up. Okay, initially both valves are closed and plunger at the bottommost position. Now plunger is trying to move up. When it is trying to move up, what will happen, well bore pressure and P cylinder pressure. So well bore pressure must be cylinder pressure. Okay, below the standing valve, pressure will be higher than inside the cylinder chamber. If it is not higher, then the valve will not be opening, the fluid will not enter here. Okay, once pressure is higher, then fluid will be entering here, and this area will be filled. Okay, then T increasing, plunger increasing, plunger moving up, that area will be completely filled. Okay, let's say after few seconds, what will happen, plunger is here and your standing valve is here. Okay, topmost position, plunger is topmost position, plunger is at top position, plunger cannot move further. So at this moment what will happen, plunger will move up, again it will try to move down. So when moving completed, so that time momentarily it will stop. Actually we are assuming both are not moving now. So what will happen at that time, standing valve, travelling valve, both will be closed. How? P cylinder, P well. Okay, so both it is not moving, so you are not creating any lower pressure here, because if plunger is moving up and there is no leakage, so in P cylinder, that area you are creating low pressure. Plunger is moving up, you are getting low pressure. Because of low pressure, well bore pressure is higher, so well bore pressure will be pushed into that cylinder area. Okay, and if plunger is stopped there, then fluid will not enter, because you are not creating extra vacuum there or extra low pressure here. When you are not creating extra low pressure, what will happen? The standing valve, it will fall down and it will be closing this inlet path, it will be sitting on the valve seat. Okay. So, that time there will be no inflow again at the top position. Okay. Now, cylinder is filled with liquid. Okay. Now, plunger will be trying to moving down, both valves are closed. So, at the top bottommost position when plunger is here, both valves closed, again plunger moved up, stopped, both valve will be closed. Now, plunger will try to move down. Okay. Now, when plunger is trying to move down, let us say after 2 seconds, plunger is here. Okay. Plunger is trying to moving down. So, what will happen? This valve, because of its own weight, that SV because of its own weight, it will be closing the path. Okay. P cylinder, P well bore. So, well bore pressure does not matter, because plunger is moving down. So, plunger is trying to pressurize the cylinder. Okay. So, P cylinder will be little bit higher than well bore pressure, and the valve, standing valve, because of its own weight, it will be closing the path. Okay. So, there will be no inflow outflow from standing valve. Now, what is happening in the travelling valve? This is travelling valve, right, TV. So, when it is trying to moving down and the cylinder is filled with liquid, what will happen? This travelling valve will be trying to opening this flow path. Okay. Travelling valve will be trying to opening the flow path, and whatever fluid is there inside cylinder, that will be inside cylinder, there is some fluid already you have taken from well bore, right. So, that fluid will be passing through the travelling valve, it will moving up. Okay. So, what will happen, and my travelling valve is here, this is closing, this is, there is no flow path here. Okay. This is almost closed and there is gap. So, this fluid will be entering to the tube. Okay. So, it will go above the plunger. This fluid will be going above the plunger when plunger is moving down. Again, plunger will be coming down to the bottom. So, momentarily both will get stopped. When both will get stopped, both valve closed. Again, plunger is moving up. When plunger is moving up, standing valve opening, bottom valve opening, it will allow fluid to fill this gap. When plunger is moving up, it is creating lots of gap. So, the gap must be filled by something, some liquid. So, liquid will be coming from the standing valve and it will be filling. Again, plunger moving down. So, that liquid, it will not go anywhere, it will pass through this travelling valve. Okay. When plunger down, it is passed through travelling valve, it will go up. Okay. So, this is the sequence. So, sequence is this: first travelling valve and standing valve close when both are nearby, travelling valve moving up, this standing valve will be opening, it will be filling this gap. Okay. And travelling valve at the top position, it will try to move down. When trying to moving down, this fluid will go up above the travelling valve. Okay. And when it is moving up, so whatever fluid is there above the travelling valve, all will be delivered to the surface. It is like this. Let us say I have standing valve, I have travelling valve here. Okay, it is fixed and it is moving like this. So, this all fluid will be going to surface your separator system. Okay, when it is moving down, when moving up, when it is moving down, the fluid will not come return back. Okay, because it is travelling valve, standing valve arrangement. Now, coming down, so well bore fluid will be taken above the plunger, again moving out, again it will be delivering. So, 1 time delivering, 2 time delivering, 3 time delivering, 4 time delivering. So, many time it will be delivering. So, and how much volume it will be delivering? So, if we have plunger area, I already told area of plunger, and you know number the stroke length, bottom to top stroke length if you know, then L. So, this volume will be delivered every time when it is pumping. So, let us say in if you have 6 strokes per minute, so 1 stroke is delivering this one. So, 6 how much it is delivering, right? 6, let us say n number of stroke per minute. So, if I have area of plunger AP, length of stroke if I know number of strokes, then I can know how much volume it is delivering per minute. Volume delivered per minute equals APLN. You have to adjust unit. Okay, AP area, plunger area, L means stroke length, N means SPM, stroke per minute. In that way you can calculate how much volume it is delivering. If it is ideal situation, there is no leakage, no other problem is there, ideally you can deliver this much of fluid per minute. You can convert to barrel per day also. Okay, so all other pump like tubing pump, top anchored, bottom anchored, thin walled, so basic formula, basic procedure is same. Travelling valve opening, fluid filling the cylinder, bottom valve opened, travelling valve moved up, travelling valve moving down, fluid is going up. So this sequence will continue and you will be delivering the fluid, and this is pulsating flow. So every stroke you are getting delivering one time fluid. When it is coming down, it is not delivering anything, again going up, again you are delivering. So this way whole system will be working. Okay, so previous so how much pump displacement or how much fluid is getting delivered? So some formula is there. If you have piston displacement PD, then piston speed N or pumping speed N or pumping per or number of strokes, you can say SPM, stroke per minute, and stroke length if you know S, plunger diameter D. So in that case you can use this formula. Here some constant term came because you are converting unit to barrel. Your data is given in inch, and if you are converting to barrel, so you have to use this constant also. Okay, so for that you have one problem with the shallow stripper wellbore is equipped with 1.5 inch insert type pump. Okay, tubing. So tubing is there, you are inserting. Okay, with stroke length about 18 inch and is pumping 12 stroke per minute. So just direct straightforward formula. You see this one 12 is given, stroke per minute is here, and stroke length S is here, and your diameter, pump diameter is plunger diameter is given here. Okay, so based on that, if you calculate, you will get 56.6 barrel per day. Now a question for you: the above problem, if my stroke length is number of stroke is changed, what will be your displacement or how much volume you will be delivering per day, barrel per day? Okay, so one similar problem I have here: a sucker rod pump well with 1.5 inch plunger operating at 20 SPM, effective plunger stroke 50. So here effective we are using. So many time our plunger stroke can be changed actually. So later we will discuss how the plunger stroke is getting changed, but assume this is a simple plunger stroke for simplification. Now liquid production rate specification is specific gravity is given 0.85, 200 barrel per day production rate. BPD here the unit is B per D I have written here. Here it is in BPD. Sometime we write BWPD, sometime BOPD, sometime barrel per day. So actually B and D is there, and in between many things they will write. So it is barrel per day. Okay, B per day, BOPD, BWPD, so many terms they will be using. But okay, so you should not say this is unknown unit. This is actually known unit. So you have to know all the terms people use in different books or different authors. Calculate the total theoretical displacement and the volumetric efficiency of the pump. Okay, theoretical displacement means there is some ideal displacement, practical displacement also possible. So later we will discuss what is the practical thing. Some leakage and other issues are there. So later will come. So again the formula is straightforward. Here you have given diameter, right, 1.4. So area you calculate pi by 4 AP equals pi by 4 diameter square. Okay, so you are getting 1.767 inch square. So N is given 20, SP is given 55 inch, Q also given 210 barrel per day. Again here I am using BD, so you can BPD. So you have to write uniformly. You should not use different units. Okay, so PD it will be coming 288. So efficiency will be Q by PD. Okay, how much theoretical, how much actually delivered. So how much delivered and how much theoretical, the ratio will be 73% if you calculate. Okay, so the very simplest formula is sucker rod pumping. Like if you are mechanical engineering student, so you know already this positive displacement pump. So there will be cylinder volume per second how much you are delivering. So that is your displacement, because you are using for oil industry, so you have to convert the unit only. And normally mechanical engineering in India, you are learning SI units, but field unit, oil and gas industry people, they will be using field unit. So you have to convert to field unit, and conversion that factors also sometimes you have to remember. Okay, if you do not remember, then if we mix up the units, then you will be having difficulty. For example, instead of 1.5 inch, if I give centimeter, then actually you have to convert to centimeter, or centimeter into inch, or inch into centimeter. All unit must be in the same format, SI or field unit. If you are using SI, then your result will be different, but final result, if I want barrel per day or something, then you have to convert everything into barrel per day. Okay, so that you have to take care. Indicator diagram for reciprocating pump. Okay, how this sucker rod pump is relevant to your positive displacement pump in you are using for other applications, in surface applications or other machinery application industries. Okay, so assume this is a sucker rod pump. Okay, and this is your plunger. This is your piston movement. Okay, this is your displacement, you can say displacement, and this is your pressure, how much pressure you are developing. So as and whenever you are designing any sucker rod pump or reciprocating pump, normally there will be one gap between piston or plunger and head, cylinder head. This is called top dead center, TDC. This is called BDC. Okay, bottom dead center. So top dead center, top, bottom dead center, dead. Okay, top dead center means piston can move up to maximum level. Bottom dead center, piston is moving, piston or plunger moving up to maximum distance. So within that distance is called top dead center, bottom dead center. But piston head or piston, this right hand side maximum, that red portion, it will not touch the TDC. Why? There will be certain gap. Okay, so this gap will not be covered by piston. When piston is traveling forward, backward, this is left to right or right to left, so it will not be touching your top dead center. Why? This is a mechanical reason. If it is touching continuously, there will be certain failure chance. Okay, so that's why the engineers or designer will be keeping a small amount of gap, and the gap traveled, the distance traveled is called swept volume. Okay, the area traveled is called swept area, swept volume. Okay, volume is area into distance traveled, that is volume. So swept volume will be less than the actual total volume. Okay, now if you have small amount of gas in that specific area, then story will be different. We are assuming, let's say everything is filled with liquid. If everything filled with liquid, and initially at the bottommost position, when piston or plunger came down and your standing valve is here, traveling valve is here, most closed location, and there will be certain mechanical gap. I already told this piston or plunger will not cross that gap for mechanical. It should not, plunger should not hit your valve cage. Okay, if it is hitting, then there will be problem. So there will be certain gap. Okay, that gap is a problem actually. We cannot make it zero. If you are lucky enough, you can make zero, then life will be easier. But because of mechanical reason, we have to give certain gap. when piston plunger very near to your valve cage, what will happen? Both valves are closed. Okay. Now piston is moving here. Let's say that pump is used on atmospheric condition. Forget about reservoir and all other fluid. Okay. Okay. In atmospheric condition, plunger is trying to moving up. So when trying to move up, what will happen? Initially, your standing valve must be opening, right? So this valve must be opening when it is trying to moving up, because you have to fill this gap, this cylinder, this P cylinder, that area you have to fill with liquid. So standing valve will be opening. When standing valve is opening, your actual pressure, that pressure, if you have one pressure gauge here, if you have pressure gauge here in the cylinder, then what will happen? When it is moving up, actually it should be less than atmospheric pressure if the whole pumping system is working the atmospheric. So atmospheric pressure 1 bar. So when it is sucking, it must be lower than 1 atmospheric pressure in the cylinder, then valve will be opening. Okay, if same pressure is there, then fluid will not enter. So when piston moving up, you are creating lower pressure, atmospheric pressure higher. So atmospheric pressure will be pushing piston, pushing the standing valve, and air will be entering. Okay, in reservoir condition or wellbore condition, plunger moving up, your wellbore fluid will be entering when cylinder pressure is lower than your wellbore pressure. Okay, so that's why piston or plunger is moving from bottom to top. So your actual pressure will be lower than this atmospheric pressure or reference pressure if I am using surface condition. Forget about the reservoir condition now. Okay, then okay, so PBDC will be here. Okay, now piston reached or plunger reached the top. Okay, in atmospheric condition. Now when it reaches the top, so cylinder pressure is very low, and it is lower than atmospheric pressure, and it got all the air. Now plunger or piston will be moving down, or opposite direction movement will start. So in that case, inside cylinder pressure will increase. So pressure will be increasing. Okay, when pressure increased, plunger moving down, pressure increased. When pressure increased, so which valve will be opening? This upper valve will be opening. Then all the air will be passing through this upper valve. Okay, or all the liquid will be passing through this upper valve. So that time your pressure will be fixed. Okay, at fixed pressure will be delivering. Okay, so what is happening? Your TV open. Okay, A, B, C, D. So travelling valve is opened. Your travelling valve is opened, delivered. Okay, after delivering, your standing valve, when you suck fluid, after sucking, standing valve close is V closes, travelling valve opens. Then travelling valve opens, then here completion, then TV closes, then standing valve opens. Okay, so travelling valve will be opening, delivering done, again is trying to moving down. So TV closing and standing valve opening, and the same cycle will continue. This is an ideal cycle, and if you have one pressure gauge inside cylinder, actually you can draw this figure, but this is ideal figure. Actual figure will be a little bit different. Now assume that there is one acceleration, because when piston is moving up and down, there will be acceleration, and standing valve, travelling valve will not be opening immediately. There will be some extra force requirement at the beginning. So what happens if I have one acceleration? So in that case, the figure will be changing like this. So figure will be changing like this. Okay. Okay, if I have an acceleration, what will happen when standing valve is trying to moving up, it will be forcing little bit more if pressure difference, let's say x, but at the beginning when standing valve is static condition, to open this, cross this static condition, actually you have to push little bit more, then it will open. So when it is pushing more, so that means your pressure will be further down. So this will be the lowest pressure, okay, when standing valve is opening, and when standing valve closing, it will be increasing pressure. And again when when travelling valve is opening, again you need some higher pressure, okay, your cylinder will be showing higher pressure, then it will open. So that's why this pressure is higher, okay. Then gradually when piston moving, it pressure will go down further. So it will form the curve like this: A, B, C, D, original curve. Your modified curve will be A dash, B dash, C dash, D dash, okay. Now you have friction, in the pipe. So what will happen, the curve will be further modified, okay. This is original one, and because of friction, the curve will be making like this, okay. Just I'll draw this, and friction also added. Because of friction, there will be some extra energy required every time, so that energy will be giving lower pressure when sucking and higher pressure when delivering, okay. This is friction effect. Friction at suction pipe is giving friction, so delivering is sucking fluid is very difficult, and this is showing friction at delivery pipe, okay. So this way the indicator diagram is getting modified. If you are having liquid, life is better, but in this world of oil and gas, when you have formation volume factor or gas liquid ratio, or some gas can come out from your fluid when pressure is lower, cylinder pressure is lower than your wellbore pressure, right? If two phase flow is creating at that point, so your cylinder will get some air, okay, air or natural gas. So that natural gas will distort this indicator diagram further, so that will create much more difficulty. If you are pumping liquid in the surface and you are pumping from wellbore, the case will be completely different. Because of this small dissolved gas will be creating multiple issues. We will discuss later why gas is a very big problem for sucker rod pump systems.